I forgot my speaker, so you won't be able to hear somebody if they're saying something.
Go back and get it.
I could. You want to take a long coffee break? So we're going to talk about circuit components. Start off with simple stuff, resistors and capacitors, and then batteries, connectors, a little bit about vacuum tubes. They're still around. You like vacuum tubes, Sid?
Oh, not really.
Oh,
It's my era.
yeah, mine too.
I still got some vacuum tube radios.
Huh?
I got a vacuum tube amplifier and I got a HQ129X that works just fine.
I think probably the majority of linears are still vacuum tubes.
Can't afford those MOSFETs.
Yeah, okay. There's basically the old, carbon composition type resistors, which you don't see that much anymore. Most of the new stuff is either a thick or thin film. Just the way they make it, they can deposit the film and, laser cut it so they can get, you can get very high precision resistors nowadays. And then there's the old wire wound, usually in power equipment, because of the fact that it's wire wound, it's actually a resistive inductor. So they don't work at high, well, they behave like an inductor at high frequencies. So you have to be very careful where you're using them. This is one of the very first resistors. And get rid of this. This is what some of the new stuff looks like Ron's surface mount. You notice the 1206 style is 1/8 of an inch or 3 millimeters. And it goes all the way down to the 402s, which I think I did a couple of those, but it's like, you really need some magnifiers to even see them.
Aren't the values still marked on them?
Usually on resistors, they don't mark capacitors. So you get all these brown capacitors, some thicker than others, but unless you measure them, if you didn't keep track of what tape you pulled them off of, you don't know what value they are. But these are 100 ohm. So why shouldn't you use a wire wound resistor in an RF circuit?
Be the coil run.
Right.
Yeah.
Unless you know what you're doing and you want the inductance. Okay. Capacitors. Majority capacitors today, even surface mount, tend to be ceramic. Basically because they're low cost, they're fairly easy to make, so they're stable, they can do fairly precision. And then the other, for really high capacitance, you still use electrolytics. I haven't seen any surface mount above about 10 microfarads. I think maybe tantalums. I haven't really run into using those. But for really high values, you still use electrolytics, which work different than a normal capacitor, where instead of you've got an electric field between two conductors for a normal capacitor, you've got a chemical reaction that's creating capacitance effect and giving you the charge on the conductors, as opposed to the electric field in there. They don't like reverse polarity. They don't like AC. We used to, in college in the machinery lab, wire one up to the power panel and throw the switch, and they would make fantastic explosions.
Yeah.
Yeah. paper flying down and that's.
Yeah, if you walk into the shop and it smells like they're frying fish in there,
Yeah.
what has happened, somebody soldered backwards.
Here's the original capacitor called a Leyden jar. And it was just a glass jar with a conductor on the outside and one on the inside. And they filled it with some kind of conductive liquid, and that's how they made the connection with that rod and the chain. And today, there's your modern capacitors. Now, this one actually is marked, but most of them I've used don't have a marking on them. They look like this brown one down here. And they came in the same size ranges from a little over an 1/8 inch down to those little 1 millimeter jobs. And those numbers represent fractions. In the case of the 1206, it means it's 0.121 inches, or approximately 1/8 of an inch. So which of the following is a characteristic of low voltage ceramic capacitors?
B.
They're cheap, stable. Surface mounts are pennies. Batteries. It's one form of power supply. Most of you are familiar with the battery in your handy talkie, or you may have batteries to power up your base station, with a solar array or something for a backup. And then, of course, if you got a mobile setup, you're using your lead acid car battery, I guess, unless you got a Tesla. So you basically have two types. You have rechargeable and non-rechargeable. You don't see nickel cadmium that much anymore, so they really haven't updated this information on the exam. Most everything now is going to be a lithium-based, lithium ion, poly, lithium, was it?
Ferrous phosphate.
Ferrous.
Yeah, also.
A LiFePO.
Yeah.
They have, all of them have a very low internal resistance, so they can deliver very high currents for a short period of time. In the case of your non-rechargeable, most of the time it's going to be a lead acid battery, like in your car, or flashlight or something where it's just a chemical, not rechargeable type. I guess I did say lead acid is rechargeable. The main thing to remember, the nominal voltage on a 12-volt lead acid battery is 13.8 volts, which is why we tend to use that for amateur radio equipment. It can be as high as 14 and a half. If you get below 10 and a half, it can damage the battery. And then there's your standard carbon zincs. Everybody knows what a flashlight battery is, or AAA or AA, or
There's also alkaline.
alkaline. Works basically the same, just different chemical process. Where the carbon zincs, I don't know, as a kid, you always used to take them apart, and get the carbon rod out of the middle, and had a zinc outer covering on it, and then some nasty stuff in the middle. I used to take golf balls apart too to find that liquid center. That was cool. So what's the minimum allowable discharge voltage on a 12-volt lead acid battery? Charlie. What's an advantage of batteries with low internal resistance? Okay, connectors. Can't see the title there. So they define electrical connector as an electromechanical device used to create an electrical connection between parts of an electrical circuit or between different electrical circuits, therefore joining them into a larger circuit. Most connectors have a gender, male and female, plug and socket. And sometimes it's removable. Sometimes the connector is permanent, like a crimp, splice, something like that. Where you require a tool for assembly and reassembly. In fact, except for the insulation displacement type connectors that's used on flat cable, you pretty much require a tool or at least have to solder connections for most of them. You should have a tool for insulation displacement, but a vise or vice grips work. We have a number of types. You've got low frequency connectors, which are in the audio range. Typically, you're going to find what's called an RCA phono connector. They've been around since, I guess, RCA started. But even modern amateur radio equipment may have phono connectors on it. You see it like an ALC output to the linear, things like that. Sometimes even the audio input. VHF connectors in the 30 to 300 megahertz range. The PL259 is what most people use. It's cheap, it's on everything. It isn't really rated for that high a frequency, actually. People even use them on UHF. It's not a very good UHF connector. For UHF, the people that want to spend the money and do it right typically use type N connectors if you're doing it outside. They're good up to about 10 gigahertz, and they claim they're water resistant because they do, the way they mate, it kind of seals it a little bit, although I wouldn't say it's waterproof. And then there's SMA, which is a little about a 1/4 inch threaded connector, which you see a lot of times inside radios to connect various parts together. It's also the connector, usually a reverse SMA on your handy-talkie for the antenna. Although some people use the regular because you have to be careful if you get an antenna for a walkie-talkie, whether it's reverse or not. There's just some pictures. They're not exactly to scale. So it's kind of showing the frequency ranges. But your SMA and the type N and the PL259 down here, and also BNC, which is up in the gigahertz range. You see that on test equipment, typically, oscilloscopes, signal generators, things like that. Small QRP type radios will typically use BNCs because of the lower power. So what's a typical upper frequency limit for low SWR operation of 50 ohm BNC connectors?
Early.
We're going to back up.
Yeah, where'd that come from?
Oh, yes, it was the chart.
Did I just miss it?
You were sleeping. 4 gigahertz BNC.
Oh, or SMB.
Yeah, but that wasn't an option.
Oh,
See, they do that to you. It's not always the most correct answer, but it's the best answer in the list of 4.
Yeah, with MCX that use it.
Which of the following describes a type N connector?
Alpha.
What's an SMA connector?
Bravo.
Yeah. Be like in Bowie.
Bravo, yeah.
Yeah.
And it's showing both sexes, male and female. Which of these, huh?
I just looked at the first answer to that last one, and I said, I always wondered what I said.
I forgot what it stands for. It's a small something.
Male and that.
Which of these connectors types is commonly used for low frequency or DC signal connections to a transceiver? Yeah. Vacuum tubes. What is a vacuum tube? I bought a book at Hamfest from this guy on hollow state devices. That's another name for a vacuum tube. Instead of solid state, it's hollow state.
Valves. Yeah, the fun with that is.
They started off with the original Fleming valve when they discovered that if you put two electrodes in a vacuum and you heated one, that you could kind of create an electron cloud and they could travel from the cathode to the anode, but only go in that direction. You couldn't do reverse because you need the electron cloud to create the free electrons.
Is that what they have to warm up?
Yeah.
To generate the electron cloud?
Yeah. And they usually put special coatings. I don't remember some kind of phosphates and things on the cathode that I guess will free more electrons than just the pure tungsten, which they used to use for the filament. In fact, originally you just had the filament was the cathode. And then they went to where you heated the cathode. The cathode was separate from the filament because you didn't get as much noise from the filament, usually AC. I'm trying to remember after Fleming, and there's just a picture of an assortment of the older miniature tubes. This is one of the bigger, I don't know if that's an octal socket or not. Transmitter tubes tended to be 4-conductor because most of them were triodes. Lee DeForest, I'm trying to remember, came up with adding the control grid so that you could actually control the flow between the cathode and the anode. So that was really the first useful tube that wasn't something other than a rectifier. So it works by applying, in that picture there, they're showing positive. Normally you'd put a negative voltage on that grid so that it's going to oppose electrons trying to make it up to the anode. So the more negative it is, the more it's going to block that flow all the way to cutoff. Whereas you've had 0 voltage on a control grid, it's like it's not there. So it's just basically back to a Fleming valve. So you get maximum current flow. If it goes slightly positive, you're going to get even more.
Question.
Normally, though, you don't have very much current on the grid. It's basically a voltage control device. Let me back up. The ratio of the anode current to the grid voltage is what we call transconductance. You also see that show up with transistors when we talk about those. It's important because there's an exam question about transconductance. So it's just that it's the essentially beta or amplification factor.
I have a question.
Question?
Yeah,
Yes, I had a question on the cathode and anode. The way I used to remember cathode and anode as to which one was positive and which was negative was the CAT. The T has a plus sign, and that would be the positive node, and the anode having the N in it would be the negative. But in that last drawing, it actually showed the anode connected to the positive of the DC supply. Can you
Correct.
clarify that?
Yeah, the anode or the plate is positive with respect to the cathode. The
that
cathode is going
different
to be either
between-
ground or negative, but the anode would be positive potential relative to the cathode.
Is that the way it works in diodes too?
Yes. In semiconductor diodes, it works the same way. We call the cathode the negative side and the anode the positive side. You're going to supply holes to the anode and electrons to the cathode.
Okay. Yeah, the way it was drawn made sense for the electron flow, but it's just the nomenclature. Maybe I'm just remembering wrongly. Okay, thank you.
Okay. After the triode, it was kind of limited in frequency response because of the high capacitance because if you got two conductors separated by something, it's also a capacitor. So they came up with the screen grid, which was like the control grid, except in between the control grid and the plate, and you apply a positive voltage to the screen grid, and it would decrease because it kind of splits it up into two capacitors in series, basically. So it reduces the capacitance considerably. So you could operate a tetrode at a much higher frequency and get higher amplification out of it than you could a triode. Can typically get reduction of 8 to 0.025 picofarads. It kind of depends on the manufacturer of the tube, spacings and things like that. And normally, as I recall, you'd run a typical tube like that at maybe 200 or 300 volts on the plate, around 80, 100 volts on the screen grid. So which element in a vacuum tube regulates the flow of electrons between cathode and plate? What's the primary purpose of a screen grid in a vacuum tube? Okay, so we learned about little on resistors and capacitors and connectors and vacuum tubes and batteries.